Hi, my name is Jim. Today's topic is operational amplifiers, and what we're going to be looking at is the frequency response and some of the artifacts that relate to it. For example, slew rate, that's how fast the output of an op-amp can change. So we're going to start here with two kinds of operational amplifiers, and here we have our frequency on our x-axis, and then on the y-axis here we have our amplitude expressed in decibels. And the first type we're going to look at is a compensated op-amp, and this is like the 741. And what compensated means is that internal to the operational amplifier has been deliberately slowed down. It's been made tame, so to speak. And what we see if we look at this is we start out with a relatively large open loop gain of 100 dB, and at a relatively low frequency here, around 10 Hertz in the example that I'm putting up here. We have our first corner frequency, and what I've done is I've drawn in the dots here which would actually indicate the point by point. So this is a Bode plot, and remember that a corner means that it's either down or up by 3 dB or 70.7%. In this case it's down. Also, if we were to draw a simple model of this, an RC circuit if you will, at the critical frequency, we would have the magnitude of the capacitive reactance equal to the resistance, and that causes a phase shift of 45 degrees at that point. So with a compensated op-amp is we can operate any gain between 100 and 0 dB with stability without any concerns. However, the price we pay for that compensation is that the bandwidth of the amplifier is reduced considerably. Now, if we look at an uncompensated op-amp that we're not going to be used because there are certain issues with it, we would find that the bandwidth is considerably greater. And instead of having an overwhelming corner frequency, in other words, when this is made, this dominates any other RC effects that are in the operational amplifier. And when I say R, that includes all kind of stuff like resistance associated with transistors, inner lead, inner silicon capacitance, and so forth. So it's a complicated thing. It's just not like a resistor and a capacitor. But this dominates every other thing inside of it. Hence, we get this straight line. Now, if we don't, or the manufacturers don't put that part in there to do the compensation, then the stray resistance equivalent and capacitance equivalent causes its own corner frequency, and as before we get 45-degree phase shifts, and as we move up in frequency, at a higher frequency there are other R's and C's that come into play, so we get a second break frequency. Now the issue is this. Here we're dealing with 45 degrees, and as we increase the frequency this moves toward 90 degrees, as this does. When we get to the second break frequency, we're adding whatever this is, approaching 90 degrees, to an additional 45 degrees. And if this here is in the vicinity of 135 degrees, we're knocking on the door of instability. So what that means in an uncompensated operational amplifier, we would have to be operating at this gain level or higher, not to avoid any troubles. Now what we would see, say if we were operating here and hit it with a square wave, would be something which would look like this. So we're starting to get into instability, and basically the high frequency components of our square wave kind of shock excite this, so we can very easily see that we're approaching instability. Anywhere below this is we're likely to have an oscillator, not an amplifier. So we're going to be dealing with compensated op-amps here, and that allows us to use a relatively simple relationship between the open loop voltage and the frequency, open loop frequency, and for the amps we're using here, 741, that's approximately 1 megahertz, and that's called the gain bandwidth product. And as you can see, the equation is quite simple here, so that's a good thing. So if we have a circuit like this, and this here is going to have a gain of 10, because the equation on this guy is the gain is 1 plus RF divided by RI, which would be plus 10, so it's a non-inverting configuration. And we wanted to know what's the maximum frequency we could expect to get out of that with a gain of 10. all we would do is we would say A closed loop times F closed loop equals 1 megahertz, and then solve for F closed loop. And what we find is that would be at 100 kilohertz. So what I can glean from that is that here's our gain of 10 expressed as a decibel as 20 dB, and we could go out till we hit the open loop gain response, and if we drop that down, what we would find with that value would be 100 kilohertz. So it's basically, as we talk about gain, I'm going to use the words kind of inappropriate, crashing into the open loop gain. So as you can see from this, if we have higher gains, the bandwidth becomes more and more limited. This does not work for uncompensated op amps, this relationship here. Now realistically, audio experts don't get into this sort of thing too much because they view things from a very different perspective. People that design audio consoles. And what they look at in a 741, say, is if we're processing signals coming off of a tape machine to burn a CD or whatever, there's a bias component that sits out there in the ultrasonic range of 40 kilohertz about, not much different than the sampling rate for a commercial CD is 44.1. And even though we have plenty of feedback here, and the feedback difference would be 80 dB at this point and 0 dB at this point. Now this feedback is corrective. It not only controls the gain, but it also reduces distortion. So for audio frequencies in here, this is fine. We have a lot of feedback, which would be the difference between this, say, and 15 kilohertz. But if we have a component sitting out here at 44 kilohertz, we don't have hardly any feedback at all. And you might say, who cares, we can't hear that, but op amps are not linear. And as a result of that, we get cross products, and those cross products can in fact come down into the audio frequency range and cause issues. So all is not well simply because we come into an area here that specifies the maximum frequency. We have to keep in mind that there may be additional distortion products if we push this to the maximum. Anyway, we're not going to be concerned about the amount of feedback and distortion. Take a look at slew rate. How fast can the output voltage of an op amp change? And it's obviously not infinite. And in the case of a compensated op amp, it's deliberately slowed down. So in black here is what we have as an input voltage. It's a square wave. And in blue, as we see the output, can't exactly follow the input. So the slew rate, the maximum rate of change, is equal to delta V over delta T. And for this example, I let delta V be 15 volts here, and delta T be equal to 10 microseconds, which would be from this point to that point. So what we would see is that would be 15 volts divided by 10 microseconds, or 150 million volts per second. Now remember, this is a rate. Now if we want to get that into a more friendly term, we can convert it into microseconds. So we'll just take our 1.5 million volts per second and multiply it by 1, which is 1 second per 1 million microseconds, and that gives us 1.5 volts per microsecond, which is usually the way that slew rate is described, as in volts per microsecond. This isn't wrong. These are the same things, but this is a more convenient term to use. And this, again, is a rate. So, we have different frequencies of interest here, and the question becomes is, will, for a given gain, is determined here, which is 50, 1 plus 49k over 1k, will the amplifier be able to produce that gain at different frequencies? So let's find out. So let's let V into our amplifier here be 100 millivolts and the frequency be 1 kilohertz, and let's find out what V out would be. Well, first we need to know the gain, and that's straightforward, it's 50. And then so I can plot that on this chart, I'm just going to take 20 times the log of 50, and that comes out to be approximately 34 dB, which is right here. So I'm now going to plot the 1K and the 34 dB and see where they intersect. And what I note is that they're well far away from the intersection with the open loop gain. That's a good thing. So what my output will be then is simply what we would expect it to be, is the input voltage times the gain, which would be 5 volts. Now the sanity check we have to do before we make that conclusion is to multiply AF, that's the closed loop gain, 50 in this case, times FF, that's the given frequency, 1 kilohertz in this case, and see if we exceed the unity gain bandwidth of the op-amp, which in our case is 1 megahertz. And actually I should have performed this test first, I did. So what we see here is the product of these two is 50K, and that's less than the unity gain bandwidth of the IC, 1 megahertz, so there's no problem. It'll work just perfectly fine at 1 kilohertz. Now let's do the same problem, only this time we'll have F equal 100 kilohertz. So here's our test. The closed loop gain times the closed loop frequency is 50 times 100 kilohertz, and this comes out to be 5 megahertz. Difficulty. 5 megahertz is significantly larger than the unity gain bandwidth, which in this case is, should have made this 1 megahertz here. There we go. So what this means is that the gain equation, that's our guy here, 1 plus RF over RI does not apply. The gain is limited by the frequency response of the op-amp at those frequencies. So to figure out what the gain can be is we have our fundamental formula here. The closed loop gain times the closed loop frequency response would equal 1 megahertz, and then all we have to do is solve for FF. Oh, I'm sorry, we're looking for A. We solve for A. So that's going to be 1 megahertz divided by our frequency of interest, which is 100 kilohertz, and that gives us a gain of 10. So our output voltage under circumstance of having an input voltage of 100 millivolts and an input frequency of 100 kilohertz will give us an output voltage approximately equal to 1 volt, considerably down from what we saw before. So if we wanted to kind of see what that would look like on the plot, we could take 20 times the log of 10, which is our gain at that frequency, and see that it comes out to be 20 dB. So that would be my green line here, and basically what happens is I would extend this over until I run into the open loop gain, and I didn't scale this right, I got it going uphill a little bit. But anyway, it should intersect right here at 100 kilohertz, and that's what that would look like. And again, as the frequency goes up, the available gain of the operational amplifier goes down. So in this case, with this frequency, is we cannot have a gain of frequency, even though we've designed it by sizing our components here to have a gain of 50. The open loop frequency response kind of wrecks it for us. So let's find the max frequency given slew rates. So we have an op-amp with a given slew rate of 3 volts per microsecond, and a signal input fastest changing voltage, we'll talk about this in a minute, is 0.5 volts per microsecond. Oh, sorry, millivolts per microsecond. 0.5 volts per microsecond. Let me verify that here. Yeah. There we go, all fixed. So what we want to do is find a closed loop given the slew rates. Now we can convert the slew rates into frequency. I'm not going to do it though. But our basic equation here is the delta V out divided by the delta T out. And you see that that is a slew rate times equals the closed loop gain times the slew rate of the input signal. Now all we have to do is solve for a closed loop. We get this guy, and populating it with our numbers, and what I choose to do here is to get rid of the microseconds in the denominator just to make it a little bit easier. So we end up with 3 volts divided by 0.5 volts, which gives us 6 volts per volt, or 6. And sometimes you'll see gains expressed as volts per volt, so that's a dimensionless number. So under the circumstance, the maximum gain we could have in the circuit at that frequency would be 6. The output would be 6 times larger than the input. So, in more time here, let's look at this. Determine the max frequency that can be used at the op-amp slew rate is 1 volt per microsecond. A little bit different. So, in this case, we have an inverting amplifier with 50 millivolts input, and our gain is going to be negative 50, and we're going to use the absolute values here, because at this gain level, we're not too concerned about phase. It's basically the same as a non-inverting amplifier. So our V out here would be 50 millivolts times a gain of 50, and we would expect 2.5 volts. So the question then becomes is what frequency can support that? Well, the governing equation for this, which again can be broken down if we elected to do that, would be the output voltage would be the slew rate, and you can see that they're directly proportional, divided by 2 pi f. So all we have to do is solve for f, and that'll give us 1 volt per microsecond divided by 2 pi times 2.5 volts, which gives us 1 volt per microsecond over 15.71 volts. Now, I've got that, and what I kind of like to do is wiggle that around a little bit. So I've taken 1 volt per microsecond, that's divided by 15.71 volts, and multiplied it by microsecond over microsecond. And what that does is that'll give us 1 volt in the numerator and 15.71 volts per microsecond in the denominator. Further, to make this clear in my mind, because I have to end up in hertz, units got to work, is I'm going to divide out the V's here, so this gives me 1 divided by 15.71 times 1 over microsecond. Now you have to remember, when we work this through here, that cycles per second is hertz. That used to be the old term for hertz. It's no longer in vogue because it was abused by engineers and technicians. What's the frequency? 1,000 cycles. What was that? Per day, per year, per what? So you got to put the per seconds in it to be considered a frequency. So hertz builds that in, so there's no issue. And what we end up with on this is it can support a frequency of 63.65 kilohertz. Okay, so let's summarize this stuff with regard to slew rate. I've gone through a lot of material here, and some of it may not seem like it's glued together very well. And let's start with a reference signal in black. It's our sinusoid. And the maximum slew rate of a sine wave comes at the negative crossover points, and that would be the maximum negative slope, and at the positive crossover points, which would be the maximum positive slope. So with regard to the black signal, we have some slew rate there, which would be the worst case for the sine wave. Note that at the 90 and 270 degree points, the slew rate is 0. Nothing's changing because the slope at that point is 0. And that's what you should look at slew rate as, basically, as a slope. Now let's say I take my little black signal here and multiply it by a factor of 2, and it gives me the red guy. And what you can kind of see here is that the slope as this goes through 0 is higher than the slope of the reference. Now this is with all due respect that it's a negative going slope, and likewise if we increase the frequency we see that the rate of change going through 0 is also higher. So what we can say about that is that the maximum output voltage that an op-amp can provide has to do not only with the amplitude of the output but also with the frequency. It's a function of both of them. So if we take a look at this in math a little bit here, we see that our signal here, V of t, and using a sine wave, is V peak sine of 2 pi f t. And if we want to determine the rate of changes, we can take the derivative of it. And the derivative operator is d dt, and the argument for it is our sine wave, and that comes out to be a cosine wave, and that equals 2 pi f times Vp times the cosine of 2 pi ft. So the point to note here is simply the coefficient of this has a function of the frequency in it and a function of the peak voltage in it. Now if we were to take a look at that from the standpoint of our cosine wave with regard to, say, the black input here, our starting signal, is we would see the cosine wave looking like this. So the fastest rate of change of the cosine wave is going to be the largest number that corresponds to this point, which is the highest rate of change in the positive going direction. And then in the negative going direction, our cosine wave, I drew it wrong. Yeah, this is going to be really good. Okay, anyway, it would be right there, would show us that this is the maximum negative going rate of change. So that was kind of confusing. But the cosine wave basically is a sine wave shifted to the left 90 degrees, and that wave shape determines the rate of change. Now notice that the cosine wave here on this guy is 0 when the sine wave is maximum. So there's no changing waveform. It's too bad I drew that wrong, but that's kind of the math behind it. So again, the rate of change as a function is a function of frequency, and it is also a function of the output voltage. So there's a lot of things that we have to be careful with when we're designing with operational amplifiers. It's just not as simple as looking at the open loop frequency response, closing the loop, and thinking all is going to be well. We have to take other things into consideration. So this will be followed by a little discussion having to do with what happens in the inverting and non-inverting input at very low gains at 0 dB. And thank you for watching. Let's take a look at the gain of two configurations of the 741. This is a non-inverting configuration here, where the output will be in phase with the input, and an inverting configuration with a gain of -1. We can see that R2 divided by R1 is going to produce a gain of 1, and it's in inverting input. And this is going to be our power supply structure here, plus and minus 15 volts. And we're going to see some interesting things. So we'll start by taking a look at the time domain. So we'll go up to simulate here, analysis, and transient. Let's fix this here. So this is going to be the non-inverting output in green, and what we see is that the input's 1 volt peak and the output is also 1 volt peak. And in red here is what we see is the output of the inverting structure, and it goes down to -1 volt as we would expect. So next, let's take a look at the frequency response of these two circuits. Again, the input's going to be 1 volt. And what we see by sweeping this from 10 Hertz way over here to 10 megahertz is that the non-inverting circuit in green hits a 3 dB point out approximately 1 megahertz. That would be this number right here, and the voltage for this would be 709 millivolts. So we're starting out with 1 volt, and when we drop to 70.7%, that's going to be our corner frequency if we were to do this in Bode plot, and that comes in at about 1 megahertz. Now, the inverting gain, surprisingly, comes in considerably less, and its output here, sitting at about 70%, is about 500 kilohertz. So the bandwidth, the unity gain on this is 500 kilohertz basically for the inverting amplifier, and 1 megahertz for the non-inverting. Now if we go to look at this in decibels, it'll be a little bit easier. This is what we see is 0 dB, which is a unity gain, and again the -3 dB points here are at 1 megahertz and 500 kilohertz respectively. So at low gains, the two configurations deviate in their bandwidth. Now let's see what happens if we increase the bandwidth, or the gain rather, and both of these circuits now have a gain of 10. For the non-inverting circuit, we have 9K divided by 1K, which is 9 plus 1. So that gain formula, AV would equal the quantity 1 plus, in this case R3 divided by R4, which is 10. Now for the inverting amplifier, the gain is negative R2 over R1, which is -10, meaning it's going to be inverting. So let's take a look at what that looks like here. So we'll go back here to the AC sweep. And what we want to be here is this guy. So what we're seeing now, and this is in decibels, so the inverse log of this here, to get it into the linear domain, would be a gain of 10. And that would be, you know, standard dB equals 20 log of V out over V in. And what we're seeing here is both of these now very closely approach the same frequency, which is 100 kilohertz, and these are going to be down by 3 dB. So since the gain is 20, the 3 dB point we're going to see here is 17. And I've got this cursor off a little bit. It's 16.6, but anyway, it's approximately the same gain as the same output bandwidth rather as the gain increases. And this would happen up to the point where we run into the open loop gain curve, which I cannot show you on this. So what this is saying is we need to be aware of bandwidth limitations when operating at very, very low gains, in that the non-inverting amplifier has considerable more bandwidth, twice as much as a matter of fact, at 0 dB as the inverting architecture. So that'll kind of do it on this. It's an interesting phenomena. The reason that happens, by the way, get out of this, is we have an attenuation factor caused by this resistor here, which cuts the bandwidth basically in half for the non-inverting. So thank you for watching.